So I've written down my maximization problem here, and now I'm going to work out the simplex method. I'm going to work out what my initial simplex tableau is. The objective function z equals 6x1 plus 6x2 goes in the bottom row and becomes -6, -6, 0, 0, 1, 0. I add my slack variables to my two constraints, and I get the first row of 2, 4, 1, 0, 0, 5, and the second row 3, 1, 0, 1, 0, 2. So now I need to go ahead and find my pivot, and notice that I have two -6's here, and our rule is we always pick the one that's farther on the left. This is going to be my pivot column. If I form the ratios, I get 5 over 2, 2 over 3, and 2 over 3 is smaller than 5 over 2, so my pivot is this 3. So that needs to become a 1. So 1/3 times row 2, put the result in row 2. My second row becomes 1, 1/3, 0, 1/3, 0, and 2/3. So I've written that up here on top, and now we need to put the zeros above and below the pivot. I'll need to take -2 times row 2 and add it to row 1. I'll need to take 6 times row 2 and add it to row 3. So here's my recipe down here below. When I work that out, the second row doesn't change, but the first row becomes 0, 10/3, 1, -2/3, 0, and 11/3. And the last row is 0, -4, 0, 2, 1, and 4. Since I have a negative indicator here, I know that I'm not at the optimum value yet. Now I take that new matrix, and I'm going to go ahead and find 11/3 divided by 10/3, 2/3 divided by 1/3. Well, 11/3 divided by 10/3 is 11/10. 2/3 divided by 1/3 is 2, so the smaller is up here where the 10/3 is. So that's going to become my new pivot. So I need to multiply that entire row by 3/10. So when I do that, I get 0, 1, 3/10, -2/10, 0, and 11/10. The other two rows don't change. So now that I have my pivot being a 1, I need to put zeros below it. So I'll take -1/3 times row 1, add it to row 2. I'll take 4 times row 1 and add it to row 3. So here's my recipe again. And when I work that out, here you see the pivot and the zeros below. The second row becomes 1, 0, -1/10, 4/10, 0, 3/10. And the last row becomes 0, 0, 6/5, 6/5, 1, 8.4. Notice that there are no negative indicators anymore, so we've arrived at our optimal solution. It probably isn't surprising that there's a connection here. Boy, that 6/5 and 6/5, that was our value for the minimum before. But remember, when we're solving a maximization problem, we go ahead and we have our non-basic variables, S1 and S2. We set them equal to 0, and we get x2 is 11/10 and x1 is 3/10. So here's that solution down here, and that leads to a z-value of 8.4. The maximum value of the standard maximization problem is the same as the dual standard minimization problem. In both cases, we got z equals to 8.4. But if you look at that tableau, our entire solution to the maximizationist problem here, remember we had that y1 was 6/5 and y2 was 6/5. Well, there they are. In other words, you're going to find the solution to the standard minimization problem underneath the slack variables, and it'll have the same z-value as the maximization problem. This means that once I've solved this dual problem, I also have the solution to the minimum problem. So we have that y1 is 6/5, y2 is 6/5, and that leads to 8.4. So our strategy for doing these problems is in step 1, we're going to find the dual standard maximization problem using the transpose. We'll solve that maximization problem using the simplex method. The minimum value of the objective function w is the same as the maximum value of the objective function z. And in step 4, we'll notice that the optimum solution is given by the entries in the bottom row of the columns corresponding to the slacks variables, so long as the entry in the z column is equal to 1. If the z value in the bottom row is not equal to 1, then we'll go ahead and we'll divide it by a number to make it 1. And then that'll give us our solution. Another caution you might want to take into account here is if you have a constraint, do not divide them through by a constant to make them simpler. Leave them exactly as they come out of the problem. Don't try and modify them. Make sure, though, you always start with a standard minimization problem before you go to the dual.